We are now going to prove another of the big theorems in analysis concerning continuous functions. This is the intermediate value theorem. And I will probably refer to this as the IVT in the future. So let's let I be an interval in the real line. And what it means for to be an interval, we'll recall. If A and B are in I, and you've got some number that's between them, then the in-between number is also in I. That is how we defined interval. And then there were those 10 options: open, closed, half open, infinite, bounded, infinite on one side or the other, or both. There were those 10 possibilities. But remember, an interval is just a set of real numbers, where if you've got two numbers in the interval, you've also got everything in between. So we've got an interval, and we're going to let f be a function whose domain is this interval and whose output is the real line. And then let's suppose that we've got 2 points in I with f of A not equal to f of B. So this is a non-trivial interval. It's not the empty set or a single point or anything. And let's pick a number that is between f of A and f of B. So we're going to let tau satisfy. Then we've got either f of A being less than tau being less than f of B, or the reverse f of B less than tau less than f of A. And the conclusion is that then there is some C in this between A and B, with f of C equaling tau. I suppose I ought to specify that A is indeed less than B. One of them has to be bigger. We'll just let A be the name of the smaller one. And what does this look like? So here's the real line. Here is our domain, which notably has to be an interval, which means you can't have any holes in it. Here's the point A, here's the point B, and then we've got f of A up here, f of B down here, or in the other direction. Then they're connected by then there's some continuous function that connects the two. And then here, or in between, is our tau. Notice that's between f of A up here and f of B down here. And then there is at least one. In fact, in this case, there are several, but the intermediate value theorem promises us at least one C that's between A and B that satisfies f of C equals tau. So let's prove this thing. So let's prove this in the case where f of A is less than our tau is less than f of B. The proof in the other case is similar, but it's just going to be a lot more straightforward if we don't have to talk about which one we want. So let's let E be the set of all points x in this interval from A to B. Because our domain is an interval, we have that every number between A and B is in I, and therefore f of x is defined for all x between A and B. So this f of x less than tau exists. And notice that A is in E, so E is not the empty set, and B is bigger than X for all X in E, so E is non-empty and is bounded. It has an upper bound, so C, the supremum of E, exists. So now here's what we are going to do. We are going to construct two sequences that are both going to converge to C. So first, we're going to notice that if n is a natural number, then C minus 1 over n, that's less than the supremum, is not an upper bound on E. So we're going to let xn be in our set at E with C minus 1 over n less than xn. If there wasn't one, C minus 1 over n would be an upper bound, but since C is an upper bound, we can write it like that. And then clearly xn is converging to C, and f is continuous at C because f is continuous everywhere, or everywhere in this interval, but C is in this interval. So f of xn is converging to f of C. And each of the f of xn's is less than tau, so f of C cannot be bigger than tau. Well, if it was, you know, you can use your interval definition of convergence and use the open interval from tau to infinity. You can use your epsilon definition if you want. And the conclusion is that at each f of xn is less than tau, so f of C, their limit is less than or equal to tau. Might be equal to, but it certainly can't be any bigger. And in particular, we have that C cannot be the number b. If c was the number b, f of b is bigger than tau, f of c is less than or equal to tau, so f of c cannot be the number b. So that's one sequence that's converging to c, and we've seen that f of c is less than or equal to tau. Now what we're going to do is we're going to let yn be c, and then we're going to add to that b minus c over n. And then, so we have that c is less than yn is less than or equal to b, and yn is also converging to c. Because b is not equal to c, we're not adding a 0, we're adding a positive number. All right. C is the supremum of E, so yn is not in E, and so that means that f of yn is greater than or equal to tau for each y, for all n. F is still continuous at c, so f of yn is converging to f of c, so we must have that f of c is at least tau. And put together, f of c is at most tau with f of c is at least tau, so we get to conclude that f of c is in fact equal to tau. And so f of c is equal to tau for some c between a and b. And notice that f of a is strictly less than f of c. F of b is strictly greater than f of c, so we cannot so we must have that c is not a, c is not b. C must be somewhere in between. And here is a corollary to the intermediate value theorem. So let's let I be an interval. And let's let f be a function from I to the real numbers that is continuous on our interval. And the conclusion is that then f of I is also an interval. We saw a theorem like that, this before, or a corollary to the extreme value theorem that said a function maps a closed and bounded set, a continuous function maps a closed and bounded set to a closed and bounded set. This, we're saying continuous functions map intervals to intervals, and the proof is pretty straightforward. Let f of a, f of b be in I, and let's let tau be any number between them, and then by the intermediate value theorem, tau is f of c for some c in I. You've got you've got c between a and b, and we decided f of a was the one where f of a was smaller than f of b, so you've got to consider two cases. And then, so tau is also in f of I. And remember, this is how we define an interval. You're an interval if a set, remember, is a set of real numbers, remember, is an interval if anytime you grab two numbers in the set and then grab a point in between them, the in-between point, it's also a set. So using our definition of interval, you've got this corollary. Now we are going to prove a big theorem. This is sort of like Proposition 1.3.3a, where we phrase convergence in terms of epsilons and n's. This theorem lets us phrase continuity in terms of epsilons and deltas. So we start out, as usual, with a point in a set of real numbers and a function from that set of real numbers into, say, the reals. Then f is continuous at A if and only if and I'm going to want to refer to this condition a bunch, so I'm going to put a star in front of it so it can say things like if the condition star holds. And this is complicated. For every positive number epsilon, there exists a positive number delta such that if x is both in X and the distance from X to A is less than delta, then the distance from f of X to f of A, that is required to be less than epsilon. And before we prove this, we'll draw a picture of what it means. So here is the graph of our continuous function. Here is A. That makes this f of A. And the idea is you or our malicious adversary, whoever, they get to pick a little interval around f of A, possibly a very small one. So then we're saying we're forcing us to be within epsilon above and below. We want to be within epsilon above and below f of A. And the response is that sure, we can do that by forcing us to be close enough to A. If we're close enough to A, if the input is close enough to A, then the output is close enough to f of A. Let's prove this. So we will start, this is an if and only statement, so we need to prove both directions. Let's start by supposing that our condition star is true. And then we need to show that f is continuous at A in the sense of our definition 1.7.1. So we're going to pick a sequence of points in our set X, and we're going to assume that xn is converging to our point A, because such sequences are part of our definition of continuity. And now what we want to show is that f of xn is converging to f of a. All right, so we're going to direct our reader to pick a positive epsilon, and then we let delta be the positive number that our condition star promises us. That is, delta is such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. And now we are going to use the fact that xn converges to a. So we recall that xn converges to a, and then by proposition 1.3.3a, there is a natural number n such that if our little n is greater than big N, then xn minus a, that is less than, and now we're going to say we want it to be less than delta, not less than epsilon, less than delta. And we're allowed to do this because we know it's convergent, so we're allowed to pick the positive number. And now we have that if n is bigger than big N, then xn minus a is less than delta, and that's by our definition of big N. And by proposition 1.3.3a, there's a big N that makes this work. So, but we know that if x minus a is less than delta, we have that f of xn minus f of a is less than epsilon, and that's by definition of delta, and that's our condition star. And then now we've seen that for every epsilon greater than 0, there is a natural number big N such that if little n is bigger than big N, then f of xn minus f of a is less than epsilon. And so put this all together, we see that f of xn converges to f of a, and this is true for all. We haven't used anything about the sequence of points xn except that there are points in x and that xn converges to a. And so by definition in 1.7.1, f is indeed continuous at a. Now we want to prove the converse direction. We want to show that if f is continuous at a, then the condition star is true. And it's actually easier to prove the contrapositive. That is, we assume that the condition star is false, and we show that f is not continuous at a. So let's suppose that our condition star is false. And so let's go through and let's remind ourselves what star says. Let's see, for every epsilon greater than 0, and then there exists a delta greater than 0 such that we have that for every number x in x with absolute value of x minus a less than delta. Then finally we have f of x minus f of a. That thing is less than epsilon. And then to negate this, to make this false, we just go through and flip each clause one by one. So for star to be false, star says something is true for every epsilon greater than 0. So for star to be wrong, we just need there to be one and positive number epsilon, such that the rest of it is false. Now the rest of it says there is a delta such that something is true. So to negate that, we need the stuff in yellow and green, we need that to be false for all delta. So for all delta greater than 0, we have that. And then this for every x in x flips to there exists an x in x with x minus a less than delta, such that, and then we negate the very last thing, f of x minus f of a is greater than or equal to epsilon. So now what we're going to do is we're going to pick some such positive epsilon, a positive epsilon such that the condition I've labeled not star is greater than 0. And then I'm not actually going to look at all deltas. I'm going to look at a very particular sequence of delta. And then if n is a natural number, then 1 over n, which I'm going to use as my delta, 1 over n is positive. So there exists an x in x with x minus a less than 1 over n, and f of x minus f of a, that whole thing is greater than or equal to epsilon. And now let's give this x a name. You're probably going to get different x's for different values of n, so let's name this one xn. And now we want to notice two things about this sequence. So the first thing is, so now we've built a sequence. These xn's are a sequence. So for each n, xn is in x, so the list of xn's that gives us a sequence in x. And notice that xn minus a less than 1 over n, that means that you can check this pretty straightforwardly with proposition 1.3.3, xn is converging to a. But f of xn does not converge to f of a. That is not true because epsilon is positive, so if xn was converging to f of a, then eventually f of xn would have to be within epsilon of f of a. So we've got a sequence that converges to A where f of xn doesn't converge to f of A. So what that means is that f is not continuous at A. And that completes the proof. We have shown that if our condition star is true, then it's also true that f is continuous at A, and if our condition star is false, then it is also false that f is continuous at A. So our condition star is an equivalent condition for continuity. What I'd like to do now is restate theorem 1.7.5, the theorem we just proved, to emphasize a few things. So let's let x be a subset of the real numbers and f a function from x to the real numbers. Then f is continuous on x. Remember, continuous on x means that it's continuous at every point A and x, so it is continuous on x if and only if for every positive number epsilon and every A in x, there is a positive number delta, and here's what I want to emphasize. Delta is allowed to depend on our function f, our number epsilon, and our point A, and then such that if x minus A is less than delta, then f of x minus f of A, absolute value, is less than epsilon. And so we draw a little picture of that at here. Don't really have enough space, but so you might have a point A here and a point B here. Then you draw the same epsilon window around f of A and around f of B. But then your delta window ends up being very wide at one place and very narrow in another place. So f is continuous everywhere on x if at any point A in x and any epsilon there's a delta that works, but you might have much bigger deltas in some places than in others. So the next definition I want to put up, this is definition 1.7.12. And as usual, we have a domain and a function from that domain into the real numbers. And then we say f is uniformly continuous on x. You don't get to be uniformly continuous at a point. You're uniformly continuous on the whole domain if for every positive epsilon there is a delta. that in this case that is allowed to depend on your function f and your number epsilon, such that if A and X are 2 points in your domain that are a distance less than delta apart, then the conclusion is that f of X and f of A are a distance epsilon apart. And I want to emphasize this is weaker, or this is a stronger condition than being continuous. Now you have to have the same delta. You have to be able to come up with one delta that works for all points in your domain. You don't get to pick 1 point per. You don't get to pick a bunch of different deltas. And in particular, you can't. This is really the situation we're trying to get rid of. This is something like f of x equals 1 over x, and our domain is the positive numbers. Then you'll notice that as we're getting closer to 0, we're getting very, very steep. So our delta windows, they're getting, in fact, arbitrarily narrow. So, you can find, so you pick an epsilon, you can find a point where, here's an even more restrictive definition. So we've got a function as usual. We say that f is Lipschitz continuous. Now remember, regular continuous by theorem 1.7.5, for every epsilon in A, there's a delta that depends on your what function f you're looking at, your point A and your epsilon, and then uniformly continuous, you're not allowed to depend on A anymore. You can't actually have your delta not depend on epsilon. And as epsilon gets smaller and smaller, delta has to get it smaller and smaller. But you can, but Lipschitz continuous is sort of almost that good. So there is a constant capital M, a positive real number, such that we're going to say if X and A are in X, then f of X minus f of A is less than m times the distance from X to A. And then quick proposition is that if f is Lipschitz, then f is uniformly continuous. And the proof of this, so we're going to pick a positive number epsilon, and then we just let delta be our epsilon over m. M depends on which function you're looking at, so delta depends on f, and delta has to depend on epsilon some way, but this is the best we're going to do. Then if x minus a is less than delta, then we can write f of x minus f of a, that's less than or equal to m times x minus a, which you'll notice is, since x minus a is less than delta, this is less than m times delta, also known as epsilon. And so that is uniformly continuous. And here is a picture of a function that's not Lipschitz continuous. Over on the left, we've got a function that's not uniformly continuous. Here is what we're trying to avoid if Lipschitz continuous. This is, for example, f of x is the cube root of x, and our domain is all the real numbers. I realize we haven't proven yet that the cube root of x really exists, but we'll get to that. We'll actually do that on the next lecture. So this is good enough for an example. And then sort of 0, 0 is kind of the bad point. If you draw an epsilon window around 0, then any delta that works there will work at any other point. But you'll notice that these rectangles I'm drawing up go from pretty fat to very tall and skinny as epsilon shrinks as we're going smaller and smaller. And then Lipschitz continuous would be, I can always put a rectangle that's different sizes but the same shape around points. So here is, so a Lipschitz continuous function. Your epsilon rectangles, say, you can always make a square work